Hello, everybody. So let me ask you guys, how loud is that for you? I imagine you can hear the terrible noise in the background. It's calming down a little bit. Okay, it's not too bad. All right, it sounds bad to me, but if it's not too bad for you guys, great. I moved my microphone a little bit away from the window, so oops. So hopefully that's helping as well. Yeah, to me it sounds super loud. All right, let's do the usual things. So here are the links to the attendance and the tutoring. Also, it sounds like they're getting close to finishing this part of what they're doing, so hopefully it'll be over soon. So here are the links to the attendance and the tutoring. Please go fill out the attendance as usual. And then let's see, what else did I want to say? So today we're focusing more on what FAM is doing. So right, Tuesdays we'll be doing MERCs, Thursdays we'll be doing FAM. Of course, if the FAM people aren't asking questions, or if the MERCs people really have a question they need to ask about, you're welcome to ask. I may kick it to later and make a video or something, but if you have, everyone's welcome. But today we'll be talking more about what FAM is doing. So what I saw from his class yesterday and on Monday is that you guys have started covering iteration by parts. He also talked about how kind of when to know when to use iteration parts versus when to use the U substitution. And then I saw today he was still covering iteration by parts, and then he did some definite integrals. And then he also, what was the other thing I wanted to say? He started talking about partial fractions of it as well. So I guess I should ask you guys, what kinds of questions do you have aside from why is my hair so giant? So now is the time to ask some questions, and here's the attendance and stuff again.
Do you have access to his notes?
One more time. Let me actually give me 1 second. Let me put in my headphones so that I can hear what you guys are saying better. Give me a sec. Okay, try asking your question again.
Do you have his notes, or should I because the problems are kind of long, or would it just be better if I read it?
Let me see. I think I have access to his notes. They're in Canvas, right?
Yeah.
Let's see. I'm assuming they're under the files. Maybe I'm assuming wrong. Can you tell me where they are?
Yeah. Or I'll just type the problem in the chat that I was.
Sure. Okay. Sorry, 1 second. Where are his notes in here? Sorry, 1 sec. Partial fractions, totally. Bunch of practice problems. Yeah. His notes, I find, I'm assuming you're talking about the notes that he writes on during class. Where are his notes? Sorry. 1 sec, guys. We'll get started here. I found the notes. Oh yeah, those are totally the notes he does from class. Okay. Sure. Okay, yeah, I see his notes. All right. So I do have his notes up if you want to refer to what he was doing in the notes, or you can type what you were going to type, which is also fine. Average daily value on specific intervals. Example 6 was confusing. Okay, let's start with example 6. I'm going to take one of these out just because I talk too loud if I have them both in. If you have a question you want to ask, feel free to ask either in the chat or by saying words. All right, cool. Let's look at example 6. Okay, a company expects its income during the next 5 years to be given by C of T equals 100,000 T for 0 less than or equal to T less than or equal to 5. Assuming an annual inflation rate of 5%, can the company claim the present value of this income is at least $1 million? Okay. So as I mentioned before, these particular types of questions, I would never actually know the formula. I would totally go look up how to calculate present value, which we'll do. I will also say, I'm pretty sure, who was it? I think it was, oh gosh, I want to say it was Sophia. I think Sophia, I think we did a problem like this the other day. Is that right, Sophia? Was that you that we did the average daily value one that was like terrible? Okay, yeah. So this is similar to that. I feel like these numbers are a little bit less awful than the one we did where we did like the average daily value over the first quarter. But we can definitely do one similar to that one as well. So I think someone, yeah, Fernanda also said average daily value on specific intervals. So yes, let me grab my pens. Also, here's the usual stuff again. And I'm just gonna apologize again to the get-go here. You guys might not hear it very well, but to me it sounds really terrible. So I feel like I'm gonna be a little bit affected by what's going on outside, but I'll just have to deal. So let's look at this example. So here's how you calculate the present value. And I'm really just looking at his notes here, although I can actually, let's see. So let me look in the textbook just because I feel like it's good to know what the actual formula is, not just what he's written there. Present value is on page 268, page 401. And I'm guessing it's definitely page 401 that I actually want. Let's take a look here real quick. Yeah, you definitely wouldn't do it that way. Okay. Sorry, 1 second. Okay, so the way you calculate present value, so C of T is a continuous income function in dollars per year. So our C of T in this particular example is 100,000 T. So that means we're earning $100,000, so 100,000 T dollars each year. So year 1, we would earn 100,000, year 2, 200,000, and so on. And then we have the annual rate of inflation is given by our percent, which in this case we have, I think it's 5%, so it's 0.05. And then finally, then the actual income over T years, so which is the present value, is given, that's different. Okay, good thing. Cool. So there's 2 different things here. There's the actual income. So actual income. And we're not being asked to calculate this, but I feel like it's worth pointing out. So the actual income is just the integral from 0 to whatever time it is of your continuous. Right. Yeah. So this is just the amount of money that you're going to make over the 5 years, or however many years. Whereas the present value is the same interval, except you also have this e to the negative RT piece going on. And basically, so not that you would need to know this really, really specifically, but the idea here is that, right, your money in however many years isn't worth it. It doesn't have as much purchasing power. Like if you have $1,000 today versus $1,000 in 2 years, the fact that inflation has happened means the money that you have in 2 years doesn't buy as much. So its present value is less than it would have been today. So that's what that e to the negative RT piece is doing for us, is it's allowing us to see what the effect of inflation has on our purchasing power. Meaning, so the bigger picture, or the kind of end result, is that this value should be less than this value. Right? This value is the amount of money we have, which we're not going to calculate. And this value here is going to be the present value of purchasing power. Here's the attendance. So let's go ahead and calculate this. So we're just going to do after 5 years. that we have. What's that? Okay, so there's the integral that we're going to do. Now, as you might be aware, this is definitely an integration by parts problem because I have t to the first, which is an algebraic thing, multiplied by e to the something with t, which is exponential. And we have different types of things multiplied together. It's usually either a u sub or integration by parts. This one's definitely an integration by parts problem. So here's kind of my preference. When I have a definite integral with integration by parts, I like to ignore the definite integral part of it until the very end. So what I'm actually going to do first, which is not what he did, which is fine. Like he did it a different way, and that's totally all right. I'm just going to do the antiderivative. So I would say, okay, what's the antiderivative for the integral of 100,000 t e to the negative 0.05? I'm going to do that, and then I'll worry about these limits of integration. And so I'm going to bring up this 100,000 in front, just because that's more. So this is integration by parts. We could use tabular, but since it's only a one-step integration by parts, and I know that because it's either the first and the e to something, we don't really have to use tabular here. So I would make the choices of letting u equal t. And now here's the thing about integration by parts that I want you guys to get very comfortable with. Once you have chosen u, and I've chosen u by the late acronym, right, I looked for a logarithmic function for u. I didn't have one. So then I looked for an algebraic function. And I considered t to the first to be algebraic. So when you have your variable to a power, like x to the third, or the square root of t, or whatever your variable is to some power, that's an algebraic thing. And that's my choice for you. So once you've chosen u, dv is everything else that is in the integral. So dv in this case is going to be e to the negative 0.5. Sorry, negative 0.05. And then we find du. So du, so the derivative of u, derivative of t is 1 times dt. And then v, the antiderivative of e to the negative 0.05 t is e to the negative 0.05 t divided by negative 0.05. Right, we've seen this before. This is one of those mini u substitutions where the integral of e to the something times x is e to the something times x divided by the something. Right, in very much the same way, we would know that the antiderivative of like e to the 7x is e to the 7x divided by 7. Right, we're just dividing by that coefficient of the variable in the power. Okay, so here's what we've got. We've got that our integral is equal to, well, it's like 100,000 times the integral of u dv is equal to u times v minus the integral of dv. Or as I often like to say, the ultraviolet super voodoo. uv minus the integral of the super dv. So uv t times e to the negative 0.05 t minus the integral of the voodoo. So that's just going to be e to the negative 0.05 t divided by negative 0.5 du, which is dt. You're not actually putting in the letters u and v when you rewrite this. It's still going to be always in terms of the variable you started with. So let's go to the other side of the board so we can rewrite this. I'm just going to rewrite this.
Sorry, for the late acronym, it's the T and E is trig and
Exponential.
Exponential.
So here's the thing. You're really never letting u, for integration by parts, you're never letting u equal the exponential thing. Right, because you're always doing something else first. there are, I think, some rare instances where you can, but they're pretty atypical. I forgot what I had here. And now I'm probably gonna simplify just a little bit first before I integrate. So I'm gonna write this as 100,000 times negative t e to the negative 0.05 t so dividing by 0.05 is like multiplying by 20, right? 0.05 is 500ths, which is 1/20th, and dividing by 1 over 1/20th, or sorry, dividing by 1/20th is like multiplying by 20. So I'd really rather write this as negative 20 times t times e to the negative 0.05. And same deal here, right? Dividing by this negative 0.05 is really like multiplying by negative 20. So I've got minus a minus, which is plus 20 times the integral of e to the negative 0.05t. All right, I'm going to integrate that, and I'm going to get the same kind of thing I did before, right? The integral of e to the something times t is going to be e to the something times t divided by that coefficient. So I'm going to have 100,000 times negative 20t e to the negative 0.05t plus 20. Antiderivative of this is e to the negative 0.05t divided by negative 0.05. Okay, so I've done the antiderivative. I'm not going to write the plus c because it's just my own kind of side work. So now I'm going to go back and say, okay, I actually want to define the integral from 0 to 5 of 100,000 t e to the negative 0.05t. Right, that was the thing we started off saying we wanted, right, this thing right here. And so now what we're going to do is we're going to say, well, it's this antiderivative evaluated between 0 and 5. So it's 100,000 times negative 20. I feel like I'm a little worried that all my numbers are negative here. It makes me wonder if I made a small error somewhere. Let me double check his work just to see if I've made a mistake. No, his is all negative too. What's going on? Am I doing something stupid? Sorry guys, just 1 second. I gotta make sure I'm not making any video here. It's hard to, oh, I know, no, we're not making an error. So what's gonna happen here, even though they're both negative, is that the number we plug in first is gonna be smaller than the number we plug in second. So we're gonna do a smaller thing minus a smaller negative thing minus a larger negative thing, which will turn out to be positive. Yeah. So even though you guys might not be able to hear that very well, it's affecting my concentration. So again, dividing by negative 0.05 is like multiplying by negative 20. So I've got 20 times negative 20, which is negative 400 e to the negative 0.05 from 0 to 5. Okay, we've got this. So plugging in 5, like negative 20 times 5 is negative 100, and e to the 5 times 0.05 is 0.25, so I've got negative 0.25 minus 400 times e to the negative 0.25 minus, then we plug in 0. Oh, sorry, this should be 100,000 times all. I'll write that again. This should be 100,000 times all of this. I'm plugging in 0, I get negative 20 times 0, which doesn't do anything. 0. And then plugging in 0 here, I get minus 400 times e to the 0, which is 1. All of that times this 100,000. And then we would calculate this, so we're going to get, so this is where we have to use a calculator, but let me simplify it just a little bit more. So this is going to be a minus is plus 400, and I'm doing it backwards. And then I've got minus this, minus this. So since these have the same power on e, I can combine them. I've got minus 100 e to the thing, minus 400 e to the thing. That's minus 500 e to the negative 1. Oh, stop. Maybe they're actually done. That'd be amazing. So then we have to use a calculator. So the way I'm going to do this is I'm going to do 500 times e to the negative 0.25, which is about 389. And then I'll do 400 minus that, and then 100,000 times that. So let's see, so 400 minus that answer is 10.599, and then times 100,000 is 1,599,000 something 60, right? Which is what he got, right? No, it is not what he got. Sorry, 1 second. What dumb thing is going on here? We did the same integral. Sorry guys, 1 second. I got 5. I got the same thing. Oh. I see. How do you get a different? What? Sorry, his number is different than mine, and it's bothering me. It either means I made a mistake, which is possible. Although, no, I think you know what it is. He's off by like, our numbers are almost the same, but our decimals just look different. Somehow he got 15.0599. Let me double check this real quick. 1 divided by 0.05 squared. That's 400, as I thought. And then, yeah, I think he made a little mistake here, because right, I'm looking at his notes. He's got 400 minus, and then he has e to the negative 0.25 times, that should be 100 plus 400, which is 500. He must have lost a decimal somewhere. So it's not, his numbers aren't quite exactly right, but it's still the right idea. So I wouldn't sweat so much that mistake. I would say that the more important part is, I imagine the big questions were about how to actually do the integral here, right? That it was an integration by parts. So are there still questions about this, or have we, so I guess I should say, right? So this is going to be approximately $1,059,960 and 80 some cents. About. So yes, I can definitely do that. Like just run through the whole thing. Okay, I'm gonna take this out because I think they've stopped. Thank goodness. I was struggling, I'm not gonna lie. So let me run over what we did again real quick. So first of all, I looked up how to do it, right? I was like, oh, I don't know what constant value is. So I know it's the integral from 0 to whatever length of time we're doing of our income, right? That's what C of t stands for. Income, which seems like a weird letter to use. Income times e to the negative RT. I plugged in my income function, which was that's my R value. So we just plug those in. And then to integrate this, we used integration by parts. So I pulled out this constant 100,000 just because I think that's better to do. If I have constant multiples, I usually like to pull them out. When I was integrating t to the negative 0.05 t, I said, well, this is integration by parts. This ended up being my choice for u. And this was my dv, right? So u times dv has to be the entire thing. Once you've picked your u, you've automatically picked what dv has to be. And so then we just followed the format. So we said, okay, u is t, then I need du, which is just the derivative. The derivative of t is 1 times dt. And then dv being e to the negative 0.05 t, the antiderivative of that is v, which is e to the negative 0.05 t divided by negative 0.05. And then we threw it all into the formula. So we said, okay, the integral of u dv is equal to u times v minus the integral of v du. Right, that's just what the integration by parts formula tells us to do. And it's really coming from the product rule, but don't worry about that. So then we wrote that out. We rewrote it. And then we simplified. So we said, okay, we'll divide by negative 0.05, right? If you, I mean, just to make sure you guys are super clear with that, right? 1 divided by 0.05 is 20, because 0.05 is 1/20th. So I just rewrote this as a negative 20, and same thing here, a negative 20. Left that as it is, integrated this, so ending up the integral of e to the negative 0.05t was e to the negative 0.05t divided by negative 0.05. Simplified again, multiplied by negative 20, gave us a negative 400 here. And then we said, okay, this is our integral. Now we're going to say, well, the definite integral, 0 to 5, is going to be that whole thing we just have here with the 0 to 5. Plugged in 5, we got some gross numbers. We plugged in 0, we got some less gross numbers. That's about it. So the thing I would say that I might do differently than a lot of people is I don't like to do like, so some people, just to kind of point out the differences, some people when they do this, if they're doing the definite integral, they at this stage say, okay, well I've got, at this stage like, okay, this is from 0 to 5, and this integral is from 0 to 5. And so they keep writing the 0 and this 5, which I just think is kind of cumbersome. Maybe they evaluate this earlier than they evaluate this, right? But then you could say this is all from 0 to 5. So the reason I do it this way is just to bypass kind of all this writing of this in here, and just to say, okay, here's my antiderivative, and now I'm going to plug in 0 and 5. So I don't have to do all this messy writing in between. And it's a perfectly legitimate way to do it. Okay, let me just give you guys the attendance one more time in case anybody missed it. And I only put it in there like 5 times. All right, let me look back and see. So, bunch of practice problems. Yeah, partial fractions, average daily value on specific intervals. So let me point out. So this would be an example. No, this is not a good example. So let's do an average daily value one, even though they're terrible. And then we'll hit up some partial fractions and probably some integration by parts as well. Again, I'll remind you guys, I know they're old, but I did make a bunch of videos on integration by parts, and I think I made some partial fractions ones as well that I posted back when the Merck's class was doing that stuff. So there are definitely examples. I encourage you to go look at them. Not that I won't do more of them, right? I'm happy to do more, but I just want to point out that there are other resources out there already that you guys can definitely look at to get some help with what we're doing. So let me find an average daily value, especially because these are definitely not ones that I would just make up on my own. Of course, average daily value. I mean, I guess maybe, even though I really don't want to, I'm going to look at that one. Let's look at the, so I know someone posted one in the discussion for class that was almost the same one that Sophia and I worked on the other day, but had slightly different numbers because that's how WebAssign or WebWork likes to do it. Okay, let's see. Canvas, Co-16B discussion. I'm so happy that they have stopped doing the mowing because it was so. Let's see. I think it was under the week 7. Yeah, I don't know. I'm gonna have to look around. Just 1 second, guys. Yeah. Okay. Emma had asked essentially the same question that I worked on with slightly different numbers. So let's look at this one that Emma had asked. I'm not going to lie, terrible, but we will work on it. So the question was actually, oh, my mic? I mean, so it might be that my mic was too close to my computer. Is that better?
Yeah, I just didn't know if it was only me or like if other people were hearing it.
Yeah, so usually it's like so I moved my mic away from my window because it was loud, but I moved it too close to my computer and sometimes it gets a little feedback. Is it okay now?
Yeah, thank you.
Perfect. Thanks for letting me know. So sorry, screenshot. I have to look at the thing. Come on. All right, so here's the question. This is problem 7 on the assignment that may have already been due. Company sells a seasonal product. The revenue R in dollars generated by sales on the product can be modeled by this. So the revenue is given by these particular numbers. They're all garbage. 430.5 times t squared e to the negative t over 30 plus 45,000, where t is between 0 and 365, right? Where t is in days. And the question is to find the average daily revenue during the first quarter. So we want to find the average daily revenue for the first quarter, which is another way of saying we want to find the average value. So when you're talking about average value, all you're talking about is doing the integral of whatever they're asking you to find the average value of, and then dividing that by the length of the interval. So just very generally, the average value of a function on an interval, a to b, is given by the integral from a to b of the function divided by however long that interval is from a to b. So in this case, we're going to take the integral for the first quarter, which is where, right, t is between 0 and 90. We're going to take the integral of this over that interval and then divide by the length, which is just 90, right? Because, so let me actually say a little more, right? If we just do the integral from 0 to 90, that'll tell us how much revenue we made over the first quarter. But we want the average amount we made per day, so we're going to take the total amount we made and then divide that by the number of days, right? So if I made, just for example, picking an easy number, let's say we did the integral from 0 to 90 and it ended up being something nice like 18,000. It's not going to be that. It's going to be way worse. But let's pretend it's this for a second. So if we made $18,000 in the first quarter, that means we made $18,000 divided by 90. That's going to be $200 on average per day. So that's an average daily rate revenue of $200. So all we're doing is taking the integral and dividing it by however long the interval is. Now the issue with this problem is terrible. So we're going to find, so we're calculating this. We're doing the integral from 0 to 90 of this 430.5 t squared e to the negative t over 30 plus 45,000. And then we're dividing by 90. So instead of dividing by 90, I'm going to write times 1 over 90. That's what we're going to be calculating. And I'm just going to show you, so a couple quick things to make this a little less terrible. I would break this up because this part here is totally kind of separate. I'm going to write this as 1 over 90 times the integral from 0 to 90 of 430.5 t squared e to the negative t over 30 dt plus 1 over 90 times the integral of 45,000 dt, 0 to 90. And this one's just going to be 45,000 when you calculate this whole thing, because in fact, let's just do this one right now since we're here. When you integrate a constant over an interval, you just get that constant times however long the interval is, right? Because you're basically saying, here's my function, right? It's y equals 45,000, and I'm integrating from 0 to 90. So the area is exactly, well, that's a rectangle. The area of that rectangle is the base 90 times the height 45,000, and then you're dividing by 90, so the 90s cancel, you just get 45,000. Or you can actually do the integration. Right, this part's going to be 1 over 90 times integrate 45,000. You get 45,000 times t from 0 to 90, and then if I plug in 90, I get 45,000 times 90. Minus 45,000 times 0. Oh, this is 0. And here the 90s cancel, and you just get 45,000. So this part here, the average daily revenue from that part of the integral is going to be 45,000. This part here, let's go find it on the other side of the board because it's awful. But I do think it's worth seeing this. We're probably not going to finish it because the numbers do get really, really gross. But it's a good example of average daily value. And then we'll do some partial fractions. Okay, so where'd you go? 1 over 90 integral of 430.5. I feel like the 0.5 is just an initial kind of like, we're going to make this just a tiny bit terrible. Okay, so just like last time, this is an integration by parts problem, right? We have a u thing, right? We have an algebraic thing, t squared, and we have an exponential thing. So I'm going to let u equal t squared. Oh, in fact, so if I was going to do this with integration, yeah, exactly. I was going to do that too. So let's do that. So let's write this as 430.5 over 90 times the integral from 0 to 90. Yeah. And so we are going to do integration by parts here. But the problem with integration by parts, well, not the problem. The thing that's going to suck about this problem is that since it's a t to a higher power than 1 times an e to the something, you're going to have to do integration by parts repeatedly. Right? You're going to have to do it for 2 times in this case, since we have t squared times e to the something. This is definitely a case where we would prefer to use the tabular shortcut method. So I'm still going to let u equal t squared and dv be e to the negative t over 30. So here's how the tabular method works. And I definitely think there's some videos of me doing this as well. So I'm going to let u equal what it would be. So u is t squared. And then I'm going to find all the derivatives of t squared until I get down to 0. The tabular method only works when you let u equal something whose derivative eventually, if you repeatedly take derivatives, is eventually 0. So it can only be some power of your variable. I should say some positive integer power of your variable. The derivative of t squared is 2t. The derivative of 2t is 2. The derivative of 2 is 0. And then if u is t squared, dv is everything else. Now, when you're writing the tabular method, we often leave off the dt part. So dv is going to be e to the negative t over 30. What's the antiderivative of e to the negative t over 30? It's e to the negative t over 30 divided by what?
T over 30.
Say that one more time.
Negative t over 30. Or
So close. You just got one extra little piece that you don't need, which is the t.
oh,
Right, we're just dividing by negative 1 over 30. Just like in the previous problem, the antiderivative of e to the negative 0.05 t ended up being e to the negative 0.05 t divided by negative 0.05. Or we're dividing by just the coefficient. So here, we're going to divide by negative 1 over 30, but it would be so much easier just to write that as multiplying by negative 30. Right? Dividing by 1 over 30 is multiplying by 30. And then when we anti-differentiate this again, it's going to be the same thing multiplied by another negative 30. So we're going to have negative 30 squared times e to the negative t over 30. And then we anti-differentiate again, and we again divide by negative 1 over 30, which is multiplied by negative 30. So we get negative 30 cubed times e to the negative t over 30. Okay, questions about this before we proceed? Here's the attendance again, just in case you need it. Okay, no questions. So then here's what, well, if there's questions, just type it in. So then the way we do this is we multiply these together and the signs alternate, right? It's plus, minus, plus. So what I want to mention here, it doesn't mean that it's a positive thing and then a negative thing and then a positive thing. It means it's plus the product of these minus the product of these plus the product of these. In this case, it's going to end up being that everything actually ends up being negative. So here's what we get. We get 430.5 divided by 90, which probably is not too terrible. Let me simplify that, because I can see that 430.5 is a multiple of 3, because the numbers add up to 12. 430.5 divided by 90. That's not as nice as I want it to be. What if I divide it by 30? 14.35. I don't know. Whatever. Fine. Let's do it like this. And then the integral of this, let me give myself more room. Sorry, things are getting a little bit out of hand here. So we're going to get 430.5 divided by 90. So the integral of this is going to be positive t squared times negative 30 e to the negative t over 30 minus 2t times negative 30 squared is 900 e to the negative t over 30 plus 2 times negative 30 cubed, which is, and I messed this up last time, so negative 3 cubed is negative 27, and then it's going to be 3 more zeros. It's going to be negative 27, 0, 0, 0. I missed one of those zeros last time. E to the negative t over 30. From 0 to 90. Okay, so I'm going to do one more step, and then if you are still working on this problem, make yourself turn it in. I'll leave it for you. But here's what it ends up getting. We get 430.5 divided by 90 times. So I'm going to plug in 90. And here's the small simplification. I'm going to get 90 squared times negative 30 e to the 90 over 30 is 3, so just e to the negative 3. And we get minus 2 times 90 times 900 e to the negative 3. And we get 2 times negative 27,000 is negative 54,000 e to the negative 3. Minus 0 minus 0 plus 2 times negative 27,000 times e to the 0, which is 1. So that's going to be a minus 54,000. Right? When you plug in 0, these ones both could become 0, but this one's not 0. Okay, so your final answer for this first part of this question, right? This is part A, is all of this plus 45,000, which is a gross problem. And then I'm not gonna lie, I think part B is even worse, because the limits of integration are not even nice, right? They are 274 to 365. So that one, it would be the integral from 274 to 365 divided by 91, because that's how many days there are in that quarter. So yeah, kind of ugly. The thing I want you to take away from this is the tabular integration. And in fact, let's do another example. So I'm going to move on. Are there any last questions about this particular awful homework problem? I mean, it's a good question. It's just the numbers are gross. Okay, let's go ahead and let's do, so I think I said this before, let me say it again. There's specifically 3 types of integrals where you can use the tabular method, and they're integrals like the following. You could have x to the 4th times sine of x, or you could have x to some power x to the 3rd times cosine of, it doesn't have to be just cosine of x, it could be cosine of like 2x. Or you could have x to some power times e to the something. And all of these are examples of integrals where you can use the tabular method instead of, I shouldn't say instead of, because it is iteration by parts. It's just a shortcut version. Right, if you're going to do the long way for each of these, you'd have to do iteration by parts 4 times, 3 times, 7 times. But these are the only types. The only types of integrals where you can use integration by parts, tabular method, is x to a positive integer power times either sine of something, cosine of something, or e of something. Those are the only 3 kinds. Let's do this one. All right, help me out, you guys. For this integration by parts problem, what's my u going to be? Yeah. Sorry, it would be x to the 7th for this one, but I'm talking about this one, which would definitely be x to the 3rd. So I'm going to have u being x to the 3rd. And now that we know that u is x to the 3rd, dv is already automatic. What does dv have to be? I'm assuming everyone's just like, I know, someone else will say it. Yeah. So for these, you do have to be a little bit careful when, especially with the antiderivative part. The derivatives shouldn't be too terrible, right? The derivative of x cubed is 3x squared. The derivative of 3x squared is 6x. The derivative of 6x is 6. The derivative of 6 is 0. You do want to write the 0 line, though, to make sure that you have the same number of corresponding dv lines, right? We need the entry that goes right there, so it's important to make sure you actually go all the way down to 0. So then we're going to anti-differentiate. So be careful, right? The derivative of cosine is negative sine. The antiderivative of cosine is positive sine. So the antiderivative of cosine of 2x is going to be sine of 2x divided by 2. Right? Just like with the e to the negative t over 31, we divided by negative 1 over 30. Here we're dividing by the coefficient of our variable, which is 2. And the antiderivative of sine of 2x is going to be negative cosine of 2x divided by another 2. So we get divided by 2 squared. Or I would probably just write 4. Let's be realistic here. And then the antiderivative of negative cosine is going to be negative sine. So we get negative sine of 2x divided by 8. And then finally, the antiderivative of negative sine is going to be positive cosine. So we get positive cosine of 2x divided by 16. Do be careful. I definitely have seen people mess up the positive or negativeness on this because they did the derivatives instead of the antiderivatives. So make sure, right? For sine and cosine, when you differentiate, you get the opposite plus or minus than you would from differentiating. So just remember that it goes kind of backwards. And then it's going to be plus, minus, plus, minus. So this is going to end up equaling positive x cubed times sine of 2x over 2. I might write it as x cubed times sine of 2x all over 2. And then minus 3x squared times negative cosine of 2x all over 4. And then plus 6x times negative sine of 2x all over 8. And then minus 6 cosine of 2x all over 16 plus c. And there is some simplifying we could do, right? We could definitely write this minus a minus would be a plus. This would be a minus, and I would reduce this to 3/4. And this would be a minus, and I would reduce this to 3/8. So there's a little bit of simplifying we can do, especially with the signs, right? Whether they end up being negative or positive. But right, that's this kind of short way of doing this integration by parts problem. Okay. Questions about this before we start doing some partial fractions problems? All right, let me erase the other side of the board. Give you guys a chance to think about that for a second. I do highly recommend using the tabular method whenever you are allowed to, right? Whenever you have one of these problems, because usually it's going to be something like x cubed or x to the fourth, or if you actually did it, you'd have to do it 3 times or 4 times, and it just is, it's really tedious and taxing. So definitely use the tabular method when you have the opportunity, because it's going to save you some time.
So I just wanted to make sure, like, when you're doing the tabular method, the u value and the dv value are being multiplied, right?
Correct.
Okay.
Right? Well, because really, so here's the thing, right? What's actually happening here, right, is in the first step of the integration by parts. This is my u, and this is my dv, right? And then the antiderivative dv is v, right? So we're getting the u times the v, just like you usually would, right? If you're integrating u dv, right? It's u times v minus the integral of v du. So we're exactly getting u times v minus the integral of v du. And so the whole rest of this is the next integration by part step. And then we do it again and again and again. But yes, the short answer to your question is yes, it's always multiplication. It's plus this times this. It's minus this times this. It's plus this times this. It's minus this times this, right? It's not this plus this minus this. That's not what we're doing. Good question. All right, partial fractions. And so I believe in this class, just to make sure, I think you don't do any of the really, really awful ones. So let's look at something like, I'm going to make something up, which means the numbers probably aren't going to be beautiful. Let's do something like 2x plus 3 over x cubed minus x squared. No, minus x. Yeah, dx. So fair warning, the numbers are probably going to suck. So first things, yeah, I want to change this. I want to make this a 2x squared. And then I'm going to compare this to another problem just to kind of point at something. So let's compare this to the integral of, sorry, one sec. 6x squared minus 2 over x cubed minus x. Okay, so looking at both of these problems, I would say, hey, these both look like partial fractions problems. I see a rational function, right? A polynomial on top and a polynomial on the bottom. And I see the denominator factors, right? Those are the two things that have to be true to be able to use partial fractions. The degree on top, has to be a rational function, and the degree on top has to be less than the degree on the bottom. And then you have to be able to factor the bottom. And we definitely can factor the bottom, right? I can see an x factors that, I probably can factors further. Now, the reason I bring up this one versus this one is that one of these, actually both of them you could use partial fractions, but typically partial fractions is what a lot of people consider like a method of last resort. Like we'd rather do almost anything else before we do partial fractions. And so for both of these, I would actually check to see if I might be able to do a u substitution. I'm going to let u equal the denominator and see what happens. So if I let u equal the denominator, my du is going to be 3x squared minus 1. And while 3x squared minus 1 doesn't really work here, right? This is not 3x squared minus 1 or a multiple of it. And I can't really manipulate this to make it work. It does work here because this here, if I factor out a 2 on top, I've exactly got 2 times, sorry, there's a dx here. 2 times 3x squared minus 1 dx over x cubed minus x, which is going to be the integral of 2, and that's my du right there. So I've got 2 du over u, which ends up being 2 times the natural log of the absolute value of u, c, which is 2 natural log of the absolute value of x cubed minus x. The point of this is that before you get going down the partial fractions path, which you often will, that'll be the right choice. You should just do a quick check to see if you let u equal the bottom, does the derivative actually equal the top or a multiple of the top? Because if it does, you can just do a u sub. And sometimes people will throw ones at you like that just to make it so like, oh yeah, this is something slightly different. This one though, definitely partial fractions. So I'm going to do the partial fraction decomposition. Well, first of all, rewriting just the integrand, right, the inside of the integral, with the denominator factored. And then 2x squared plus 3 divided by, if I factor this, I can factor out an x. I'm left with then, let's see, that's going to be x times x squared minus 1. And x squared minus 1 factors further as x minus 1 times x plus 1. So after I've written that out, I then write it as some constant over the first piece, some constant over the second piece, some constant over the third piece. Right. Each different factor in the denominator gets its own coefficient on top of it. And then the reason we do this is so that we can then multiply. I'm going to erase that over there. We can multiply this whole thing by this common denominator, x times x minus 1 times x plus 1. When we multiply this by the left-hand side here, we're just going to get the numerator, where we get 2x squared plus 3, because the entire denominator cancels out. On the right-hand side, when we multiply this here, the x cancels, and you're left with pen on your hand. You're left with a times x minus 1 times x plus 1. When you multiply here, the x minus 1 cancels, and you get b times x plus 1. And when you multiply here, the x plus 1 cancels, and you get c times x minus 1. Whenever you do this partial fraction decomposition, once you multiply both sides by the common denominator, you shouldn't have any more fractions. Right? You should get rid of the entire denominator. Sorry, there's like I hate when this pen on my hand. It's terrible. Okay. And whenever you have ones like this with linear factors, right, where you've got x or x minus 1 or x plus 1 or 2x plus 3 or 5x minus 2 or anything where it's just something times x plus some other constant, you have this method of picking convenient values of x. I'm going to pick values of x that make something 0, right? So if I pick 0, these terms will be 0. Pick 1, this will be 0, and that will be 0. If I pick negative 1, this and this. I'm essentially just picking the values that would have made these denominators 0. So I pick 0, I pick 1, I pick negative 1. Picking 0, I'm just going to plug in 0. 2 times 0 plus 3 is 3. A times 0 minus 1, 0 plus 1. And I'm not even going to write the other ones because I know that b times 0 and c times 0 are both going to be 0. So I end up getting negative a equal to 3. So a is going to equal negative 3. And then we repeat the process. I'm going to pick x equal to 1. So now I have to plug in 1 everywhere there's an x. I get 2 times 1 plus 3, which is 5. On the right hand side, I get a times 0. I get b times 1 plus 1, so I get b times 1 times 2. And I get c times 1 times 0. So 2b is equal to 5. So b is equal to 5 divided by 2. These numbers are not as bad as I thought they were going to be. I lucked out. I made some lucky choices. So then for x equal, why did you guys figure out x equal to negative 1 gives us for c while I use the rest of them real quick? So go ahead and figure out what c is. It should be, I think it should be also 5 halves. So hopefully that was correct. Well, let's double check and see here. So I plug in -1, I get 2 times -1 squared, which is 2 times 1. So 2 plus 3 is 5. On the right-hand side, it's not dependent on. I get a times -2 times 0, b times -1 times 0, and c times -1 times -1 minus 1. So I get c times -1 times -2. So 2 times c equals 5. So c is also equal to 5 times. Okay, so we're not done yet, right? We then have to say, all right, that means we can rewrite the integral. We're going to say, okay, my integral, well, this fraction is equal to these fractions. I'm just going to write these fractions with the values I found for a, b, and c. That's going to be -3 over x plus 5 halves over x minus 1 plus 5 halves over x plus 1. And then each of these is not too terrible because they're all going to have natural logs, right? The integral. So when I write this, I'm really thinking of this, and you can write it like this. I don't think you need to. It's -3 times 1 over x. It's 5 halves times 1 over x minus 1. It's 5 halves times 1 over x plus 1. So that, sorry. So when I integrate this, I get -3 times the integral of 1 over x is the natural log of the absolute value of x. And the integral of 5 halves is the natural, the integral of 1 over x minus 1 is the natural log of the absolute value of x minus 1. And 5 halves times the integral of 1 over x plus 1 is the natural log of the absolute value of x plus 1 plus e. So that's how that type of thing works. Okay, so questions about this? All right, let's do at least 2 more of these. Let me see. To do that. Okay.
I have a question.
Go ahead.
I think I just figured it out, but I just wanted to make sure, how did you get, or take the way that you got like the 3, 5, and 5, like before you,
Sure.
is because you plugged in 0 and 1 and -1 into the top, right?
Well, so basically I'm looking at this equation, right?
Uh-huh.
And so when I pick x equal to 0, I have to plug in 0 for every instance of x. So I'm plugging in 0 here, I'm getting 2 times 0 plus 3, so I'm getting 3 on the left hand side.
Okay, that's what I thought.
Yeah, so when
and then for that part.
Yeah. So when you're using this method that I call picking convenient values of x, you always are plugging in your convenient value for all of the x's.
Does it matter like what numbers you use?
It does matter. You want to pick the values that make lots of things 0. So I wouldn't want to use something like 4, because 4 doesn't make anything go away. I want to pick values of x that basically leave me with only one of these unknown constants behind.
Okay, that makes sense.
Good. Let's look at another example. Maybe one that's slightly, slightly easier. Integral from, I mean, we could do let's do a definite integral. Why not? Let's do the integral from, let me make sure it's not going to suck. Do the integral from 3 to 8 of 1 over 7 over x squared minus 4. Okay. This one's going to be a little bit different, but we're still going to do, so if I was doing this, I would do the indefinite integral first. Actually, no, I take that back. I would just do the partial fraction decomposition. So and I know I can use partial fractions because, again, that's a rational function, right? Polynomial on top, polynomial on the bottom. And the degree on top is definitely less, right? The degree on top is 0, the degree on the bottom is 2. And I can factor the denominator. This x minus 2 times x plus 2. All right, that as a over x minus 2 plus b over x plus 2. And I'm going to multiply both sides by that common denominator. So multiplying this through, I get 7 on the left. I get a times x plus 2 because the x minus 2's would cancel. I get b times x minus 2 because the x plus 2's would cancel. So let me ask you guys, what is one convenient value of x I could pick to plug in? 2, exactly. What's the other convenient value I'm going to pick? And negative 2, yeah. So yeah, if I pick, now something slightly different about this problem. In the previous problem, there were x's on the left we had to plug in for. In this problem, there aren't, which isn't really that different, but it just need to be aware of, right? You only plug in x where you have an x. So for this one, I'm going to have 7 equal to a times 2 plus 2 is 4, plus b times 2 minus 2 is 0. So I'm not going to write that. So a is going to be 7/4. It's divided by 4. Plugging in negative 2, I still have 7 on the left. On the right, I have a times 0 plus b times negative 2 minus 2 is b times negative 4. So I get b equal to negative 7/4. So then we can rewrite our integral. This integral now is going to be the integral from 3 to 8 of a over x minus 2 minus b over x plus 2. And in this case, since the coefficients happen to be essentially the same or opposite to each other, I would probably do one more thing before integrating. I'd probably factor out the 7/4 and write it as the integral from 3 to 8 of 1 over x minus 2 minus 1 over x plus 2. And just because it's a little bit nicer. Not required, but it's fun. So then we get 7/4 times the integral of 1 over x minus 2 is the natural log of the absolute value of x minus 2. Minus the integral of 1 over x plus 2 is the natural log of the absolute value of x plus 2. From 3 to 8. 7/4 times all of that. So we get 7/4 times, plug in 8, you get the natural log of 6 minus the natural log of 8 minus, plug in 3, you get the natural log of 1 minus the natural log of 5. Natural log of 1 is 0. You can probably just leave it like this. That's going to be 7/4 times the natural log of 6 minus the natural log of 8 plus the natural log of 5. I would probably leave it like that. You could combine it all into one logarithm and say it's the natural log of 6 plus the natural log of 5, which is the natural log of 30, and then minus the natural log of 8 needs to be divided by 8. So that would be, you could totally write this as the natural log of 6 times 5 over 8. 30 over 8 reduces to 15 over 4. You could do that. It's not really necessary. I started making noise again. I mean, I understand, right? It's work, but it's loud. Questions about this?
Wouldn't the log of 8 be log of 10?
So,
Because it's the natural log of x
you're
plus 2.
right. I definitely made a mistake there. Yeah, good call. Good eye. Right, plugging in 8. So I get natural log of 6 minus natural log of 10. Thank you. Excellent. And then plugging in 3, I get 1 and 5. So that's right. So really, this would be, actually makes it nicer, I think. Because then it's going to be natural log of 6 times 5 over 10, which is just the natural log of 3 times 7/4. Yeah, even better. Good call. All right, let's do at least one more where we have a repeated linear factor. Yeah. And actually, so this one's going to have a couple interesting aspects to it. My life. So I will point out, I am excited about what is going on because we're having our backyard landscaped. It was a field of wheat, actually it was a field of beautiful mustard, yellow, pretty, nice. Then they came and sprayed it and it was dead. And now they're cutting it all down, and they're gonna build us a yard, which would be great because then we can go outside. Sorry, I'll show you. Maybe I'll zoom on my phone one of these days, and I can show you guys the yard once it's all done. Let's see. I had something in mind. Let's do this. Well, on top. Sure. That might be worse. Let's just make it. Sorry, let's just make it x. No, let's do that. Okay. So this problem is a rational function. Sorry, is an integral or rational function. The bottom does factor, right? I can factor an x squared, but it's not proper. The degree on top is not less than the degree on the bottom, right? The degree on top is equal. So if the degree on top is equal to the degree on the bottom or bigger, before you can actually go ahead and use partial fractions, you have to do the polynomial division. So here's what we're going to do first. We have x cubed plus 2x squared plus 1 divided by x cubed plus x squared. So I wrote in the division symbol, right, the dividend is the thing you're dividing into, x cubed plus 2x squared plus 0x plus 1, because I want all the missing powers of x just to make my life easier. So then I'm going to say, what do you multiply by x cubed to get x cubed? 1. 1 times x cubed is x cubed. 1 times x squared is x squared. Subtract. I get x squared. Bring down the 0x, even though I probably don't need it. And then x cubed is bigger, like it's a higher power than x squared, so I stop. So what this tells me is this fraction here can be rewritten as this quotient plus this remainder, quotient, remainder, divided by the divisor. So that's the first step to doing this problem if the degree on top is bigger than or equal to the degree on the bottom. Okay. So then if I was doing this, I'd probably say, well, this is going to be integral of 1 with x plus this thing here, which I'm going to rewrite as x squared times x plus 1. I was worried I accidentally picked something where things were going to cancel. Nothing cancels here, right? You cannot cancel any of this stuff. So we have to move forward with partial fractions. So here's my partial fraction decomposition. X squared plus 1 over x squared times x plus 1. Okay, this is a little bit different than the previous ones. In this case, since we have a repeated factor, right? We don't have a linear factor x, we have x to the second power. You have to have that power of your factor and every smaller power. So I need something over x squared, but I also need something over just x. So I need a over x, b over x squared, and c over x plus 1. Just to kind of clarify this in case it's unclear, if I had, let's say I was doing a different partial fraction decomposition. Let's pretend like we had something, I'm gonna make it extra terrible. Let's say I had something like 2x plus 1 over x plus 1 to the 4th times x squared. That's enough garbage. Let's say x cubed. Let's say we had this. This is going to have 7 pieces. So I would write this as, well, I have x plus 1 to the 4th, so I need up to the 4th power and every lower power. So I need x plus 1 to the 1st, b over x plus 1 squared, c over x plus 1 cubed, d over x plus 1 to the 4th. And the same sort of thing for x cubed. I need every lower power as well. So I would need e over x. The next letter of the alphabet is f over x squared and g over x cubed. So whenever you have a repeated linear factor, meaning a linear factor to a higher power than 1, you need all of the lower powers of that as well, which is why we have x and x squared. Okay, I'm going to erase this, but if there's questions about it in the future, let me know. So what we're doing here is saying, all right, again, we do the thing where we multiply both sides by the common denominator. And I should point out, the reason you want all these lower powers is because when you add these fractions together, their common denominator is still x squared times x plus 1. Right? I'd multiply this by x over x and x plus 1 over x plus 1. I'd multiply this by x plus 1 over x plus 1, and this by x squared over x squared. And they all have the same denominator of x squared times x plus 1. So multiplying both sides by that common denominator, x squared times x plus 1. When we multiply the left, we always just get whatever the numerator is. On the right, we get, well, so one of the x's would cancel, and I get a times x to the first times x plus 1. For the b term, the x squared would cancel, and I get b times x plus 1. And for the c term, the x plus 1 would cancel, and I get c times x squared. And now we're going to pick convenient values of x. So what are the two convenient values of x to pick here? What are the values of x that make things go away? 0 is definitely one of them. What's the other one? 1 is not, but it's a good guess. Definitely, -1. So I plug in 0. Again, plugging in 0 for every x. I get 0 plus 1 on the left. I get a times 0. I get b times 0 plus 1. And I get c times 0. So b equals 1. Great. Plugging in -1. -1 squared is 1, plus 1 is 2 on the left. Plugging in negative there, I get 0 there, I get 0 there, and I get c times -1 squared. C times 1 is 2, so c equals 2. And now you have options, because we've run out of convenient values. So there's one of two things can be done. If there's only one value left to find, right? We found b, we found c, there's only a left to find. Then you can just pick any other value of x. It's not my favorite way of doing it, but we totally can. So you could pick x equal to 1 if you wanted to. So I'm going to show you this, even though this isn't what I usually do. So if you pick x equal to 1, you would have 2 on the left. You would have a times 1 times 2, so 2a. You'd have b times 2, but b is 1, so I'd have 1 times 2. And I'd have c, which is 2, times 1. So I could solve for a, right? Subtract, right? 2a equals -2. So a equals -1. And that's perfectly fine if there's only one thing left to find after you've run out of convenient values. But if you have a repeated factor that's to a higher power than 2, you're going to have more things to find. And so the more standard way of finding the leftover ones after you've run out of convenient values is to use a method that's called equating coefficients. So, excuse me, if we look at this equation here, what we're saying here is this second degree polynomial on this side has to equal this second degree polynomial on this side. And for polynomials to be equal to each other, they have to have the same coefficients on each of the distinct powers of x. Meaning, the coefficient on x squared on the left is 1. The coefficient of x squared on the right has to be 1 as well. I'm running out of room. Where is this? Over here. So here's what I'm going to say. So I'm going to equate coefficients. And I typically like to start with the highest power I've got. So for x squared, on the left I have 1x squared. On the right, if I multiply it out, I would have ax, so a times x squared. And I wouldn't have a b times x squared because it's b times x and b times 1. But I do have a c times x squared. So what that tells me is the amount of x squared on the left has to equal the amount of x squared on the right. But then I already know what c is. C is 2. So 1, yeah, okay. I was writing this wrong. 1 equals a plus 2. Subtract 2, -1 equals a. So that's the way I usually find anything left after I'm done using my convenient values, is I just equate coefficients. All right, so now we've got a, b, and c. So let's rewrite our integral. Let me go to the other side of things. So right, here's what we had. I know we're just about out of time, so let's just finish off this problem real quick. If you need to go, you're obviously welcome to go. Do make sure you fill out the attendance. Also, as a reminder, I do have office hours today from 1:30 to 2:30. The link is in Canvas under the announcements, I believe. So if you want to come, please feel free. Okay, so where were we? We were at this. So we've got our answer being x plus the integral of x squared plus 1 over x squared times x plus 1. And that's going to be x plus the integral of, it was a over x, and a ended up being, so sorry, it's a over x, and a is -1, b is 1, c is 2. I know literally there's other things I forgot already. B is 1, c is 2. Then we're just going to integrate this. So the integral of -1 over x is going to be negative natural log of absolute value of x. The integral of 1 over x squared is not the natural log of x squared, because 1 over x squared is x to the -2. We just use the reverse power rule. That's going to be x to the -1 divided by -1. Plus 2 times the integral of 1 over x plus 1 is the natural log of the absolute value of x plus 1. And you could leave it like this, or you can simplify it. The only simplification I would do is I would probably rewrite this as -1 over x. But that's not really necessary. All right, that is all we have got for today. Yeah, we'll see you guys later. I'll see you next week. If you have questions, always post something in the discussion or send me an email. And if you want to come to the office hours today, please do so. I will be there. Take care.